Well, hello, hello. Okay, so now we're going to start getting into some of the nitty gritty. The way we've been calculating limits so far have been kind of just based on prior knowledge and a lot of sort of I don't know tedious techniques. And so I want to introduce you to several ways that we can calculate limits in a more efficient way and using a more algebraic approach. All that algebra you've been learning for the last 2 years is finally going to come in handy. Okay, so the first thing I need to talk about is functions that agree with each other almost everywhere, meaning two functions that are basically the exact same function except that maybe there's 1 or 2 points that are different. For example, here are two functions. What do they have in common? How do they differ? I will let you graph these yourselves in Desmos or calculator, whatever you want to do. But graph these two functions and talk about how are they similar, how are they different. Okay, perfect. Welcome back. So as it turns out, these two functions are the same function, except for one small thing. F of x, the function on the left, has a hole in it. You can't see the hole, but it is there, I promise. There's a hole at the point -1 comma something. I think -1 comma -2. So you can't see it, but it is there, I promise. G of x, on the other hand, is just a line. It's just, it's a totally continuous, beautiful line. No problems, no holes in it or anything. So it's basically the exact same function. The difference is that f of x is the same line, but it's got a hole in it. Okay, what about these two? Why don't you graph these two functions in Desmos or something and tell me, again, what do they have in common? How are they different? Okay, welcome back. Again, these are identical. These functions look exactly the same, except again, there's a hole in one of them. There's a hole in the function on the left. There's a hole at 4 comma something. 4 comma, I think 1/4. But yes, that is the only difference. They are the exact same function. One of them has a hole in it. The other one does not. Okay, so when this happens, we say that these two functions are equal to each other almost everywhere, or they're equal to each other at all but one point. And so this leads us to a very, very important proposition that's going to be exceedingly useful in this class. And it states the following. If you have two functions that are equal, so this is a little bit weird, strange wording here. This is very math heavy, but basically it's saying, so if f of x equals g of x, meaning your two functions are the same function, for every x not equal to a, meaning they're equal to each other at all but one point, and that point is at a, when your x value is a, so it's at the point a comma something. In the last example it was 4 comma something, and in the example before that it was the point 1 or -1 comma something. So if this is true, if the functions are the same at all but one point, it turns out that the limits are the same, which is very, very wonderful because taking the limit of one of them is hard because we can't use direct substitution, but taking the limit of the other one is easy because we can use direct substitution. So going back to our two examples, this is the first one. Again, we've got f of x and g of x, right? These functions are the exact same function except that the function f of x has a hole at the point -1 comma -2, and g of x does not. Fortunately, our proposition tells us that the limit as x approaches -1 for both of these functions must be equal to each other then, because they're the same function. These functions are equal to each other except for at one point when x equals -1. But that doesn't matter. The limits are still going to be equal to each other. So the limit as x approaches -1 of f of x is equal to the limit as x approaches -1 of g of x. Which function would you rather plug -1 into using direct substitution? If you pick f of x, you are wrong, because if you plug -1 into the f of x function, you're going to get 0 over 0. But if you plug -1 into g of x, oh my goodness, this is just -1 minus 1, which is -2. A piece of cake. So the idea here is that you find a function that is basically the same function as the one that you started with, and then that new function that you have is what you can use direct substitution on. You can plug your number in there directly. Okay, we also saw that these two functions were identical, except for when x was equal to 4. The f of x has a hole in it at 4 comma something, and g of x does not. But again, thanks to our proposition, we know that the limit as x approaches 4 for both of these functions must be equal to each other. And again, I'll ask you, which function is it easier to plug 4 into? It's not the first one because we get 0 over 0, but if we plug 4 into the second function, direct substitution, we get 1 over root 4 plus 2, right? Just plug 4 in for x. And this is going to work out to be 1/4. So the limit as x approaches 4 for the first function is equal to the limit as x approaches 4 for the second function, which is easy to calculate, and that's just 1/4. That property is wonderful. It's going to save the day so many times for us. So the big question is, how do we find these things? How do we find these functions that are basically equal to the original functions? And the answer is not going to be showing up in this video, unfortunately. Tune in to the next videos to see how we're going to use algebra to find these new functions. Get excited, people. I know you are. All right, fantastic. See you soon.